No, it's not just a different bed length. I am not Nick Schmer. But I am also very happy to introduce Emily Martin, our colloquium speaker today. Emily is one of the rising voices in the domain of planetary science, especially as far as icy satellites and their tectonics is concerned. Though she said she might have to go to a little bit more traditionally rocky material, which would be the moon, but
change is good, right?
That's pretty good. Emily studied at Wheaton College in Massachusetts, and those who know why I'm making the distinction know why I'm making the distinction. And the others can ask us afterwards in our after colloquium party. She also spent a little bit of time at Northwestern, getting a master there, and then got a PhD from University of Idaho with Simon Kattenhorn, who was also one of the big guys on icy satellite tectonics. And for probably a couple of years or something, she's been in the Smithsonian Institution in Washington at CEPS, the Center for
Earth and Planetary Studies.
Earth and Planetary Studies in the Air and Space Museum, where she's a professor. Well, today she's going to tell us a lot about those icy satellites, especially Saturn's ocean worlds from deep time to now. So, Emily,
hey, thank you. I appreciate that. And I'm really excited to be here, and I really enjoyed meeting all of you guys today, and I think I had a really fun time being able to talk about icy satellites. I actually gave, some of you know, I gave a talk on Wednesday to the tri-state astronomers. And that was a really fun group to give a talk to, especially when you're talking to people who think more about stars and the cosmos and the universe, and all the really cool stuff that's been going on, especially with the really cool recent news about gravitational waves. But I study a different part of the solar system than I think a lot of people think about. So what I want to try and do today is I tried to build a talk that if I lose you with my plots and my models, you're going to have a really awesome slideshow right now of all the stuff that I find really exciting about the outer solar system. So I don't study Jupiter, I don't study Saturn, I don't study Uranus or Neptune. I study all the things that go around those things. I like things that are made out of water ice because, believe it or not, if you don't know, these moons of Saturn in particular are made out of mostly water ice. So while it looks like rock, or it looks like maybe something I don't know if you could say that this looks like, any of these look like Mars, there's a really bad Photoshop job. This is not my forte. This is 3 different moons of Saturn. They're all made out of water ice, and they're all really weird looking. So this is one of my favorite montages that was ever made. This is a poster you can actually download from the Planetary Society. This is made by Emily Lakdawala. She's made a couple of these. They're actually really cool. When I saw this, I had to print it out immediately and put it on my wall. It literally sits above my desk. I actually use it as a reference because sometimes I don't remember all of the names of these moons or their relative sizes, and that's the beauty of these things that she makes, is that they're all to scale. So note, none of my plots are to scale.
Sorry to interrupt so
Sure.
early on,
I'll forgive you.
Are all the Uranus satellites dark?
They are quite
They all
dark.
have a low albedo?
I actually don't know the albedos of the Uranian satellites relative to those of the Saturnian satellites, but I do know that of the Saturnian satellites, Enceladus is one of the highest albedos in the solar system. And then Iapetus has one of the darkest albedos in the solar system on one side. So I actually don't know their relative albedo with respect to some of these other places, and I don't know whether or not she stretched these in such a way to try and highlight some of the details on the surfaces, so I'm not going to answer that question. But I love showing this because Save the Moon, although as Laurent mentioned, I'm going to be starting some work on the moon here soon. Other than the moon and Io and Vesta, arguably all of these other places are made predominantly out of water ice. So all the geology that I'm going to be showing you today is ice and not rock, but at the cold temperatures of the outer solar system, this ice is behaving an awful lot like rock. So we can use a lot of the principles we understand about how rock behaves here on Earth and apply it to the outer solar system.
Couldn't we suggest, though, that many of them have a density of 2?
Many of them do have a density of 2, especially when you start looking at Kuiper Belt objects like Pluto and Charon and Triton, because of the larger rocky fraction that they have within them. But still, the surface geology that we are observing are predominantly made out of water ice. So I broke this up into a few parts. And the first one should be hopefully the fun part for everybody is, why are icy satellites so cool? And it's in part because so many of them are or were warm at some point. Now this is Enceladus, which is what I've done most of my work on, but it's really inspired me to start comparing Enceladus to some of the other, maybe less interesting to the general public moons, because I think they all inform one another. I think comparative planetology is so important when you talk about the outer solar system, because our data sets are so limited. They're resolution limited, they're coverage limited. We don't know what all of these things look like all the way around. This is a really big challenge, and so we have to rely on similarities and differences between these different places in order to learn more about them. So we think they're cool because they're warm. So this is Enceladus. This is its south pole. These are jets of water shooting out of the south pole. Later on, I'll show you the E-ring, but this water is shooting out of Enceladus. It's going into orbit around Saturn, and it's making one of Saturn's rings called the E-ring. Enceladus is about the size of Washington State. It's very, very small, but somehow it maintains enough heat to maintain what we think is a global liquid ocean underneath an icy shell, and it's somehow making this plume. We haven't figured out all of those dynamics yet, but this is one of the things that gets me really excited about icy satellites. So within part one, I have a few lessons I want to impart. And lesson one is that all the cool kids are now calling these ocean worlds. So I grew up calling these things all icy satellites. The word of the day is now ocean worlds. This is language that Congress has now put into place, that NASA has been directed to create an ocean worlds program. For people like me who grew up in the age of Mars, when I started doing planetary science, it was the age of the Mars rovers. And icy satellites were really sort of the ones that, like, there was just a handful of people doing. And now when I talk to people, it's like, oh gosh, you study Enceladus, you study Europa. Wow, I always knew those places were really cool. I don't know if I believe that they always thought they were really cool, but when you look at places like Titan, now this is a radar image. Titan's atmosphere is really quite thick, so Cassini's camera cannot penetrate that atmosphere. So what you're looking at here is a radar image. So you're looking at bright areas are rough, dark areas are relatively smooth. But if these look like dunes to you, it's because they are. These are in the equator of Titan. I'll show you some pictures of Titan's lakes later. It's the only other place in the solar system with liquid on the surface. Lesson 2, icy satellites are really interesting. Many of them are geologically active. You've already seen a picture of Enceladus's plumes, but I want to give you a little bit of a roadmap of some of the vocabulary I'm going to use for Enceladus, and talk a little bit more about why Enceladus is really a very interesting and dynamic place. So this is the south polar terrain, so Enceladus is sort of tipped up a little bit because the south pole is centered right in here. These large blue cracks, those are called the tiger stripes. Those are literally where the material is coming out of Saturn's south pole. What's even more interesting is that this is Enceladus's north pole. You'll notice there are no plumes there, there are no tiger stripes there, and there's an awful lot of craters. So we believe the north pole to be much colder, much less active. I don't have time to get into it today, but I'm going to argue that these features that are going through the North Pole are in fact very young, so there's something very interesting going on into the North Pole, but that's another talk that we don't have time for. But if you want to ask me questions about it later, I'd be happy to talk about it. Another active place, like I said, is Titan. Now you can blame Enceladus and Titan in part for the ending of the Cassini mission. Cassini was so successful that it found these geologically active worlds that were really interesting astrobiological targets. And as Cassini was running out of fuel, they really needed to make certain that they had control of that spacecraft and they could terminate the mission with control. They did not want Cassini landing on Enceladus or Titan and contaminating those planets, so that when we were able to finally return and actually make astrobiological measurements, we weren't measuring our own bugs. We wanted to keep these places really pristine. So Titan's really spectacular because it's got these seasonal changes that you can detect in the lakes, and there were so many flybys of Titan that you were really able to actually get these time-lapse images, which you just, outer solar system stuff, this just doesn't happen. You see this maybe on the moon, you maybe see this kind of stuff on Mars. When you look at, oh, there's a new crater. We never saw that crater before. We can tell that that's a new crater. You don't see that kind of stuff in the outer solar system because we don't have that kind of data collection rate. And so you can actually see in this ellipse, there's actually some changing that's going on in here for about over the course of about 7 years. It's really pretty spectacular. So this dark area that you're looking at here, that's actually a lake. And that these things over here that sort of look a little bit like river valley networks are in fact river valley networks. So lesson 3 is that ocean worlds are interesting because they likely host or hosted habitable environments. And I kind of talked about this a little bit already. And people mostly think about places like Enceladus and Titan as the places where you see the most potential for astrobiology. Titan because you've got hydrocarbons on the surface, you've got liquid on the surface. Enceladus because you've got water at the near surface that you can see because of the plumes coming out of the South Pole. But there's also these bodies, Tethys, Rhea, and Dione. Again, these are all bodies of, that go around Saturn, and they all have some degree of wispy terrains. And fun fact, this is all the same hemisphere. This is all the trailing hemisphere, I believe. Don't quote me on that. It might be the leading hemisphere. I can double check. So you can see Dione certainly has the most activity that has been preserved on the surface. This is all a series of faults and fractures preserved. This is called the Wispy Terrains. It was called the Wispy Terrains because when Dione was first seen by the Voyager spacecraft, they had this very, have you ever seen fresh snow blowing in the wind? It's got this sort of ghosty effect to it. They actually thought that maybe some of this material was sort of cryovolcanism, some kind of volcanic deposit. They couldn't really see the linearity in these features. But they also saw something like this on Rhea in the Voyager images. The contrast is much, much starker, and you just see this really bright, fuzzy spot. And then also in Tethys, you can see this sort of canyon that runs along here. So we have these wispy terrains, and one of the things I've been trying to work on is what is causing this fracturing in these icy shells. And one of the ways you can do it is if that ice shell is deformable. And the easiest way to make that ice shell deformable is to put a global ocean underneath it. So these places, all of these icy worlds have some level of astrobiological potential. And when you look at all of these icy worlds and you look at the activity that's been preserved in those ice shells, you start to think, wow, at some point, these places had liquid water. And liquid water, it might be cold at 0 C, maybe there's some salts in there that kind of change that temperature. But they all have water at some point in their history. So we want to know how long we had that water to know whether or not these places might have been liquid, rich, long enough to maybe be places where habitable environments had grown. And I just want to show you this really quick. This is Dione, and I'm going to be talking about these wispy terrains a little bit later when I actually show you some of the data that I've been working on. But you can see in this close-up, there's this just series of really nice normal fault scarps in this area. So this is predominantly extension. You see mostly extensional tectonics in the outer solar system, not a lot of evidence of compression, which is something that people are actively working on because you can't just extend an awful lot of stuff without having any kind of compression. But we see mostly extension. And lesson 4 is that icy satellites just help to keep the outer solar system weird. I don't know if you guys are all from the East Coast and had never heard about keeping Portland weird, but that's where this was from. Or Austin, yeah, keep Austin weird. So while these next couple of places that I'm going to show you aren't necessarily considered really high priority astrobiological targets, I think they're really important when you're looking at the continuum of these diverse worlds. And so I always love showing this one because people really like it. Whenever I talk about icy satellites, people said, oh wait, is that the Death Star one? Most of these moons have really large craters like this on one side of them, so you can pretty much orient any of them to make them look like the Death Star. But Mimas is always one that kind of gets forgotten because people think it's just cratered, there's nothing else interesting going on there.
Would they to scale and also albedo?
I don't know the answer to that. That is a great question, and now I'm going to have to look it up because somebody else is going to ask me. Nobody's asked me that yet. That's a good one. So Iapetus is a really interesting one. I worked on Iapetus while I was at Northwestern, and one of the things that is intriguing about Iapetus is that this darkness and this brightness is real. It might be stretched a little bit in order to enhance that contrast, but the contrast between the dark side of Iapetus and the opposite side, which is very, very bright, is a real contrast. It's one of the starkest contrasts in the solar system. And what's also really interesting is that there's this ridge that goes all the way around, and this is in fact the equator. It's not like 10 degrees off. It's the equator. It's the weirdest place, and this is kind of an enhanced perspective shot that's been exaggerated a little bit, but you can actually see, I mean, it's a mountain range. And if you want to talk more about that, we'll talk after. I didn't have time to fit all of the things that I'm excited about icy satellites in, but the last one that I really wanted to show you is predominantly ice. It's not all ice because it's a little bit closer to Saturn, but it's pan. Called the empanada, the space pierogi, the space dumpling, the space ravioli, take your pick depending on your favorite cuisine. But one of the things that I'm really interested in pan, and I just can't quite get around my brain, are these really interesting scarps here. It's just so small, it's hard to imagine that you've got these tidal forces acting on it, and you've got this strange ring around it that people think is material from the rings collecting along its equator, and it's sort of sloughing this material onto the surface. But if that's loose material, how is it not just sloughing down and landsliding? I mean, that looks like a really steep slope. Yes, sir?
I'm sorry, how big?
Pan is about 30 kilometers in its largest dimension. In another PowerPoint presentation, I have that information, but it's tiny. This is within the rings. It's one of the shepherding moons. Of course, there's like the shepherd moons, and then there's like shepherding moons that sort of have a shepherding effect. So it's not one of the official shepherding moons, but it's right. And there's other ones that have this kind of ring feature. So we're going to move into part 2. That was the cool stuff. I'm going to show you more cool stuff, but it's all relative, right? So the second part here is dating is hard. One of the things I'm really interested in is deep time. And I want to compare the deep time, the early history of these bodies to understand the early oceans and the current histories of these bodies to decide whether or not is an ocean still there. If it isn't there, when did we lose the ocean? How did we lose it? Did it simply freeze out? What's going on with these places? So I'm trying to understand the timing of the internal evolution of these bodies, but I'm doing it from looking at the surface manifestation of these processes. And so I'm trying to make a lot of inferences. And so this thing that I'm working on, and I have a confession to you guys, I haven't presented this stuff yet to in this story, in this way. So hopefully it's gonna work out. So the first thing I needed to tell you guys about is how hard it is to do dating. Crater dating is a thing that people know about. It's really very good on the moon, in part because we have samples from the moon, and so we can date the sample and we can count the craters and we can make a really nice calibration. It gets harder when you move away from the moon. When you get to the outer solar system, all of a sudden we're not entirely certain what our crater populations are, what our cratering rates are. And so there's people like Michelle Kirchhoff at SWIRI in Boulder, who does what I think is some of the best crater counting in the outer solar system, and she's so good at being transparent about how hard this is. So these different colors that I had here, these are all the different terrain types that Michelle has put together based on the different crater densities and some surface morphologies. What I want you to note is, so here are the different terrains. Let's just focus on FT, which is this big green region, which is where Dione's Wispy Terrains are. Follow this over, and you've got case A and case B. These are just different crater models that she uses. Case A, results aren't good enough for her to even give you a number. Case B, the results are, within the age of the solar system or more, right? So you've got, depending on the population of craters you're looking at in this region, depends on the result that you get, and the error bars on this are pretty spectacular. There's a researcher in Japan who's been trying to develop a new technique based on individual fractures and the population of craters underneath and on top of those fractures. I haven't really done a lot of work to assess whether or not this is a really robust technique, but he's actually putting ages of the wispy terrains sort of, he still gets this really big range depending on case A and B, which are the same as Michelle's. And then his new technique is this one over here, and he's coming up with these incredibly young ages of less than 1 billion years old. If he's correct, that's really interesting, and it fits in with what we're trying to do here. But this is hard. So what I'm trying to get across here is I often get questions like, well, when did that happen? And I'm like, well, it happened before this. They're like, well, but when did that happen? And I was like, I don't know, sometime after that. It's as good as we can get. This is also a perennial problem on Enceladus. We have better coverage on Enceladus than some of the other icy satellites, in part because we know Enceladus is geologically active, and that immediately makes everybody want to look at it. So when we did a lot of the flybys, when Cassini did a lot of flybys, they made sure to have extra flybys of Enceladus to make sure that they could get as much information about it. So again, Michelle broke up the different terrains just on this hemisphere because the data at the time wasn't very good over here. And what I want to point out we're going to look at these blue terrains, RP4, which are these ridged plains, and then we're going to look at these cratered plains. And so the different parts of Enceladus I'm going to talk about are the south polar terrains, the tectonized terrains, and the cratered terrains. There's just 3, it's not too bad. And so Enceladus is a little bit like a tennis ball. It's got these cratered terrains that sort of go all the way around, and then it's got sort of these patches of tectonized terrains on either side with the south polar terrain underneath. So it looks kind of like these very hemispherically symmetric terrains, which is interesting. And again, you can look at RP4 right here, which is these sort of mid-color blue. And you can look at her case A and case B, and you see 1.6 to 0.05, which isn't so bad when you look at the average and just ignore the error bars, which are, off the page. So again, this is a really hard thing to do. So I'm going to focus a lot on today relative ages. And by relative ages, I'm going to call them really old and really young. So we're not talking about a very high detailed age scale here because I don't have it. And I'm hoping that we can do a little bit of a better job with some of these things that I've been trying to work with. So I want to look at changes through time, which means we need a time machine, and we're going to use fractures to do it. Fractures behave in relatively predictable ways. They interact with each other in relatively predictable ways. So usually, assuming your resolution behaves, you can generally get a sense of what happened first and what happened second. So what I want to introduce you to are really young and really old features on Enceladus, Dione, and Rhea, all moons of Saturn. And I want to give you a sense of how we can tell what's really old and what's really young, especially if we do not have a cross-cutting relationship. So Enceladus, really old. We have really old troughs and we have really old ridges. How do we know they're really old? Well, as you can look in here, we've got some of these features here. Troughs, ridges. If the round things are craters, if they look like they're sticking out to you, they're really craters, so they're sticking down. So anything that sticks out at you is actually a down. Anything that's a down is actually an up. How's everybody feeling about that? I know that's really confusing, but all the craters look like domes to me. So if they look like domes to you, you're right on board. So anything that looks up is actually a down. So you've got these troughs right in here. They're very wide. You can see that they're very smoothed. And you see all these little lines that are running on top of them. Those are features called pit chains. We'll talk about those a little bit later. Those fall into the really young category on Enceladus. But you can tell that these things are overprinted by both craters and pit chains. They're broad, they're smooth. You can't see a lot of information. You can't see a lot of detail. They're cross-cut by a lot of things. These are really old. Really young. These are features called pit chains. Pit chains cross-cut everything. They cross-cut what's called the south polar dichotomy, which is this band that sort of encapsulates those tiger stripes where the plume is coming from. We know those to be really young because there's no craters on them. We have pit chains crossing those. The tectonized terrains, those are also really young. There's very few craters there. We have pit chains crossing those too. And then, of course, we have pit chains all over the cratered terrains. So for Enceladus, pit chains are really young. So we're going to do Dione. We're going to start with Dione, really old. Again, remember, things with craters on top of them, things that are really broad, things that have been really smoothed out means that they're not fresh. They've been heavily degraded. And we have different kinds of things like ridges, and I'm going to show you a topography topo image of this much later. You've got a ridge here. You've got this trough. Troughs were probably graben at one point in their lifetime, but we can't tell at this stage because all that sort of detail has been eroded away. And then we've got scarps, and this one's kind of hard to see, but there's a scarp there. Trust me. Don't you love scientists who say, trust me? Hi. Yes.
About the, what is the dominant process for the erosion of these features? Is it like micrometeorites?
Impact cratering.
Okay.
I'm just learning about sintering. There's some sintering that happens. I don't understand sintering. I'm just learning about it, but it's definitely a thing. It's definitely a fact. With this many craters, you're going to have some kind of regolith generated. And so you're going to have, on Enceladus, of course, you've got the plume dumping material onto the surface at all times. Shameless plug, see Martin et al. 2017 if you want to know more about that. But cratering, impacting, sintering, you've got some regolith being generated. There's some regolith processes there that I don't understand. They happen at really tiny scales, and that is somebody else's expertise. But yeah, so cratering's a big one. And then Dione, really young. These are the wispy terrains. Remember those big bright blobs on the surface of Saturn? Saturn. Dione, and then Rhea and Tethys also had these, but we're talking about just Dione right now, and you can see they're really bright. And that brightness is really important. Enceladus is spewing its material all across the surface of many of these moons, and you can actually detect it in some of the different wavelengths. And so when you see these really bright scarp faces, you know that they've definitely been younger. I haven't met anybody who can do good processing on this to actually look at the absolute albedo of these scarp faces and start age dating them that way, but if somebody knows how to do that, you should do it because I think it would be very cool. So you can actually see these really beautiful scarps, and then you've got these really beautiful graben that are forming on Dione, and you can see that they're just cross-cutting all of these craters. There's very few craters that land on top of these scarps, so really young. Rhea is really hard. Can you guys see it? Can you see a fracture in this image? It is not this. This is an image seam and my rudimentary, yes, exactly, you've got this. Really hard. They're really hard to see, right? Rhea doesn't have as much preserved. Rhea doesn't have nearly as much tectonism as Dione and Enceladus, but this tells us that there just maybe wasn't a lot of tectonism going on really early, or somehow it was small enough that all the impacting has gotten rid of it. And then this is really young. And again, if you compare this to really young on Dione, these don't look quite as young, right? There's some more impact craters on top of them. Maybe they're a little bit more eroded by impact cratering. So I couldn't even guess about whether or not the timing of wispy terrain formation on Rhea and Dione were happening at the same time. I'm not even going to go there. But they don't look quite as fresh as everything else that we see on, say, Dione. But relatively speaking on Rhea, this counts as a really young population of features. So part 3 is we want to look below the crunchy ice shell. So I not only am using fractures as a way of trying to determine what's relatively older and what's relatively younger. What is representative of the ancient tectonic history of these moons, but what is also representative of the recent tectonic environment. And we need to use fractures in order to do this, because fractures allow us to make some inferences about what's going on below the surface. So we use what we can see on the surface to infer what's going on underneath. So faults and fractures actually let us probe into these moons. And again, we're interested in the interiors of these moons because the more we can learn about the ice shell, the more we can learn about how much ocean there might be down there. How thick is that ocean? Is that ocean freezing? Is that ocean actually forming? So there's some kind of warming process and that ice shell is actually melting a little bit. We don't know what's going on. And so we're trying to piece together what's going on with these interiors, which means oceans, right? And how they've maybe changed through times. And this is one, does anybody want to guess what moon this is? I've had a lot of people be like, what moon is that? It's Enceladus. Nobody ever shows you that view of Enceladus because they want to show you the tiger stripes because they're blue and they're fun to look at. But this is a really fun shot of Enceladus, and I like it because you can see all this jagged limb, which is all real topography. That was just a side note. Okay, oceans can help fracturing happen. That's an important lesson. So if we're going to use fractures to understand the interiors, we need to know how we can do that. Part of how we can do that is by looking at the patterns that the fractures make on the surface. So I'm going to read this to you because these I worded very carefully. Tectonic deformation in icy shells. It manifests itself oftentimes as fractures. These fractures are forming in response to stresses. Those stresses can be used to identify, the stresses create fractures. Fractures can make a pattern on the surface, and they don't always look like a pattern, but when you make detailed observations of those fractures, you can actually discern a pattern that you can then use to backtrack and make inferences about what that stress field was at the time. There's different kinds of stress fields. I don't want to get into all of them because I'm only going to really talk about a couple of them, but I want to get you thinking about what I really mean by a stress field. So let's look at the colorful ones first because I think they're just a little bit easier to think about. Things like polar wander, right? We have that on Earth, right? The pole is changing its position. That produces, predictably, zones of compressive stresses, which is these blue areas, tensile stresses, which are these red areas, and compressive and tensile regimes in these purple areas. Now, I know that that's not entirely predictive because it doesn't tell you what orientations of those features you should actually expect in those areas. But what it is telling you is that if you see predominantly compressive features in the polar regions and you see some kind of combination of those features in the equatorial regions, maybe we're looking at a polar wander scenario. What I'm most interested in are these diurnal tidal stress fields and these non-synchronous rotation stress fields. And what I want you to think about, maximum tension is in red. Fractures form perpendicular to the direction in which those stresses are going. So think back to like intro physics when you draw the force diagrams and the arrows. That's really what we're talking about here. So we have max tension in red and maximum compression in blue, so features are going to form perpendicular to the blue arrows. So what we really care about with icy shells, for the most part, is extension. So pay the most attention to the max tension, which is red. So when you look at these arrows, you can kind of get a sense of what kind of features you might see where. It's a lot easier to see in the non-synchronous rotation stress field, where I've conveniently drawn the theoretical fracture patterns you should see in a non-synchronous rotation stress field, which are these black arrows. Diurnal tidal stress is in non-synchronous rotation. I didn't tell you guys how that worked, did I? I don't think I have I didn't put that figure in. Sorry. So, diurnal tidal stresses. Enceladus is in an eccentric orbit around Saturn, which means it's not perfectly circular, which means Saturn is raising a tide on Enceladus. So think about, instead of looking like a sphere, it's looking a little bit more like a football, and that football's long axis is pointing at Saturn. Saturn is pulling on Enceladus. This happens on Earth. The moon is pulling on Earth, and Earth is pulling on the moon. But because Earth has liquid on the surface, it's a lot easier to pull those oceans. So actually the tides of the oceans going back and forth is really just the moon pulling on us. So think of it the same way. Saturn's pulling on Enceladus. Enceladus is really tiny. Saturn is really big. So you're kind of elongating Enceladus. Enceladus is doing it to Saturn too, but it's negligible. And because Enceladus is in an eccentric orbit, it means that pull of Saturn on Enceladus is changing just a little bit, which means that long axis of that football-shaped Enceladus, highly exaggerated, is kind of flexing back and forth like this. That generates heat. Now, and that would be where you get diurnal stresses, is that back and forth, that heat that's being built up. Non-synchronous rotation has to do with the decoupling of the ice shell from the rocky core by a global liquid water ocean. Now, all of the satellites of Saturn, most of the icy satellites in the outer solar system, are synchronously locked with their parent planet. Same thing, Earth and the moon. We always see that same side of the moon, always. If you have non-synchronous rotation, if that ice shell is decoupled from your core, that ice shell is a little bit free to move over long time scales, like millions of years, hundreds of thousands of years. That ice shell can actually rotate a little bit faster than everything else. It's imperceptible with the kinds of data sets we have, but that actually can make the ice shell go up and over that diurnal tidal bulge, and that builds up a lot of stresses too. So these are the two types of stress fields that we're going to be talking about the most. Predominantly non-synchronous rotation, and I'm going to have all the cheat lines in there for you, so you can always match up any line I draw with the black line in the vicinity, and you're going to be good. So that's the match we're looking for. Did either of those make sense? Okay, good. I have a lot of nods. Non-synchronous rotation. Somebody used to build me a model. That one's a hard one. Okay. So, really old and really young fractures. I actually mapped out all the really old fractures on Enceladus. And I looked at them. And when you look at faults and fractures, things that form close to one another, that are parallel to one another, that look an awful lot like one another, probably formed under the same stress field at approximately the same time. Right. So what you see are the grouped and the ungrouped troughs. I get very creative with names sometimes. So the grouped troughs are all the different kinds of troughs that I found on Enceladus, ancient troughs, the really old stuff, that were all parallel to one another in a very spatially constrained area, which made me say, you know, those things all probably formed in approximately the same time. All the ungrouped stuff, as you can see, doesn't really fit any kind of pattern. So that made me think, I wonder if this is two populations of really old things. Let's see whether or not these really old things fit any kind of stress field that we know about. So this is where the black cheat lines come in. So what I did is I took the black cheat lines from the non-synchronous rotation stress field and I laid them on top of a map of the really old features that I found. And you kind of move it back and forth like this until you see whether or not you can find a match. And I'm going to argue that this is pretty good. I have to do more work to actually put some, bounds on this and actually tell you how good it is. But I would argue that it's pretty good. You can see these blue group here, they're all kind of going in this direction, and that kind of matches where these black lines would be, which is where you would expect to find some surface cracks. And you can see that all of these actually kind of wrap around in this direction, which made me think, gosh, these things are all looking like they're forming in sets. Things that are parallel with one another, they look like each other, they probably all formed under the same stress field. If you look at it within the context of a non-synchronous rotation stress field, it looks like maybe they sort of all formed around the same time, which is interesting. But if that's the case, I don't know if you noticed, this is not the same organization of these fractures, right? I kind of shifted them around. This is actually the present day configuration of where the non-synchronous rotation stress field would lay on top of a bunch of these other features, and you can see that that doesn't look very good. But that's so we can do this match if we take Enceladus' ice shell and we back rotate it 120 degrees. Non-synchronous rotation is a very convenient scapegoat for trying to match your observations to a model. So I get a lot of skeptics, and I'm with you. but it's a good match, and I think it's a place to start. I'm not going to tell you that this has to be the answer, but I think it's a pretty good place to start. And when you look at this grouping of features, I can't make that match with anything. So are we seeing two different periods in Enceladus's history where we have two different stress fields that are dominating at two different times? That's what we're trying to get at. And this is both within populations of features that are really old. So I want to show you really young. Now this is part 2 of my pit chain work. The paper is really close to being done, I promise. So you can question the paper. How's that? So this is all of the pit chains across Enceladus's surface. You can see that they are predominantly within the crater terrains. Okay. And I built a little strat column here. I don't get to build strat columns very often. So I use this. This strat column is built based off of the best cross-cutting relationships I could find. So not every single one of these features cross-cuts every single other feature that I can tell you 100% that this is where they fit. But generally speaking, this is where they are. So we can see that the youngest features are sort of these green and yellows, and these blues and purples are kind of the older features. So I'm going to show you how I think maybe this happened. Now keep in mind, this is the crater terrains, this is crater terrains, this is crater terrains. So all the gray stuff here is crater terrains, all the black lines are those cheat lines for you. So anytime you see a black line, that's where you might expect a crack to form or a pit chain to form in this case. So we started with blue. Now you can see there's no black lines here. If we could create black lines here, we would need higher stresses in here. So these black lines aren't showing up here because it's hard to put north-south fractures on the equator. No matter what kind of stress models you're looking at, this is a pretty hard thing to do. But I just want to tick through this so that you can see how other sets work. So the next set are these purple ones. You can see they fit pretty well in here, maybe not so good up in here. The red ones, they show up, they fit really pretty well in here. And remember, we're going up this strat column here. Then we get these orange ones that are forming right in here, and you've got this other side. So notice they're hemispherically symmetric, which is the other thing that's really interesting about the non-synchronous rotation stress field. It's hemispherically symmetric. When I made this strat column, I did each hemisphere independently from one another. And then I said, what was the first set to form? What was the second set to form? What was the third set to form? And I was like, well, that's interesting. They're all pointing in the same direction, but they're on opposite hemispheres. So that was another thing that was very convincing for me. And then we've got, what color? Yellow. Fits pretty nicely in here, and then you have green. And there's parts where this doesn't always fit really perfectly, but my animations are primitive. So these are pit chains. These are really young features. These are also showing a relatively good match. Not a great match. Still have to back it up with a little bit more work. But a relatively good match with non-synchronous rotation. So we see in the really old fractures, we maybe have some good evidence for non-synchronous rotation. We also have that evidence with the really young features, but we still got that ungrouped group of really old stuff that maybe doesn't quite fit so well. But what's interesting and what we're seeing on Enceladus is that we maybe have some kind of episodic changes in this stress field, and we don't know what that's telling us yet, but we're starting to think about maybe one of the reasons Enceladus is preserving such a complex history is because that history was really complicated. We have different stress fields dominating at different periods of time. So I'm trying to reproduce this on Dione as well, and I can only show you the really young stuff right now. So what I have here is a map of all of the scarps and graben within the Wispy Terrains, and they kind of have this really cool loopy pattern in here. And I did this a little bit differently. I still compared this to a non-synchronous rotation stress field, but I also compared it to a diurnal tidal stress field. And I did it a little bit differently in that I took all the orientations of the different features and I averaged them into different bins. So it'll be a little bit easier to kind of see them match up. So the red in these figures are showing you the features that I mapped, and the black is showing you the sort of average orientation in that location bin. So the first thing I want to do is compare it to non-synchronous rotation because we think it's a thing that's happening in the outer solar system. We seem to have evidence of it happening on Enceladus. You could definitely argue maybe or maybe not on Europa, one of Jupiter's moons. And you can see that for the most part there's a pretty good fit for some of these features. There's a little bit of an offset, but generally speaking it's not such a bad fit. And it looks pretty good for a diurnal tidal stress field if you look at it in periaps. But if you want to see a really bad fit, look at it in apoaps. I'm not telling you that this is a smoking gun. I'm not telling you that this is exactly how it's happening. I'm telling you that I think these are pretty good guesses for what's going on. And when you look at cross-cutting relationships of Dione's wispy terrains, they're completely ambiguous, which tells me that those wispy terrains are forming at approximately the same time. All of those features that look like they're all in random orientations, when you start looking at them within the context of these different stress fields, it actually looks like perhaps those ambiguous cross-cutting relationships are telling you that they're all related to one another. They're all forming during the same event. So we can use the patterns of fractures from different populations to start talking about what kinds of stress fields were dominating at different periods of Enceladus's history, at different periods of Dione's history. And the harder part is looking at this for Dione and Rhea because I didn't put them in here, but if you look at the global distribution of the ancient features, there's just such a low concentration of them that when you try and make these matches, there's just very few features to look at and actually make some comparisons with. So I'm going to switch gears a little bit here because this is sort of one of my ways of trying to get at this idea of deep time and looking at what kinds of changes might be occurring. Because the stress field, when we model the stress fields, we actually look at sort of these different layered structures of these icy satellites. We say this is how thick the lithosphere is, this is how thick the ocean should be, this is how big the core is, this is how dense it is. We give it some rheological parameters to generate these stress fields. So we're making a lot of, we're waving our arms an awful lot, right? Models are helpful, they're not always correct. So we wanted to make some other kinds of measurements to see how well we're doing with our models. Are we making good estimates of the ice shell thickness at the time that we're trying to model? Are we making good estimates of these rheological parameters? The models are going to be able to tell us about what might drive these different fracture populations, but we want to do more. We want to talk about the ice shell and we want to talk about the heat flux. And it occurred to me that a lot of people have been looking at this, especially on Enceladus. A couple people have looked at this on Dione. But there was an opportunity on Dione in particular where somebody had done this on had looked at the thickness of the brittle portion of the ice shell, right? Because the ice shell, the top part's going to be really brittle, but as you go deeper and you get a little bit warmer and you get closer to the ocean, that ice is going to get a little bit softer, a little bit more ductile, and those fractures can't propagate into that ductile stuff. So if you get a fracture that you can somehow infer is penetrating all the way to the base of the brittle portion of that ice shell, you can actually say how thick you might think that brittle portion of the ice shell might be. From that thickness, you can actually make an inference of a heat flux. And so what I wanted to do is figure out whether or not we could actually detect a difference in the brittle ice shell thickness and the heat flux on these different bodies of features of different ages. Does that make sense? So if you look at a really old feature and you can infer how thick the ice shell was and you can infer what the heat flux was, you look at a younger feature and you do the same thing, can you see a difference within the bounds of how much arm waving you had to do in order to get that information out of the data? So I want to start with Enceladus, and I want to give you a little bit of a context for how big some of these numbers are. This is the south polar terrain. This is observations from the CIRS instrument, the Composite Infrared Spectrometer on Cassini. They found, Howitt et al. Found heat fluxes of like 400 milliwatts per meter squared. That's a lot. If you were to do this heat flux measurement of Enceladus and you were just heating it up with radiogenic heat from the rocky core, you're talking like 2 to 3. So 400 is a lot. Now that 400 seems really high. It's averaged over this whole area, but really it's important to look at this figure rather than this figure. This was one of the press release figures that I think was always really striking because this is what they were expecting the temperature distribution of Enceladus to be, and this is what they found. There's this concentration in the South Pole, which since we've seen the plumes makes perfect sense, except for that doesn't make perfect sense. Like, why is it like that? But when you actually break down this number into these higher resolution observations, you can see that rather than this entire region pumping out all of that heat, it's focused along the tiger stripes. It's focused along the places where that material is coming out. So keep this number in mind, 400, just to give you a sense of how hot or cold, or how high or low the heat flux measurements that I'm about to give you, right? And then keep it in your head. If it's just radiogenic heating, if nothing else is going on, it's 2 to 3. So this is a really big number. And I put this is just cool. Okay, so Enceladus is tectonized terrains. Remember, this is a really young area. There's very few craters. You can see some craters, but most of these craters are actually cratered terrains. This is tectonized terrains, something I didn't talk about. The boundaries between these terrains are like, it's like somebody just cut it. So this group, the Giza group at DLR in Germany, used topography to infer the elastic thickness. And they come up with an elastic thickness of about 2 to 3 kilometers. Then you have their heat flux calculations, which come up to about 200 to 270. It's about half of what we're seeing in the South Polar terrain. But that's a lot more than 2 to 3, right? I mean, this is high. This is really high. Now, this is done on an individual feature, which is really the kind of direction I'm going into. But within the literature, there was another group, Bland et al. In 2007 did something just before they did, and they actually modeled the formation of these terrains rather than sort of making topographic, I mean, they made topographic measurements, but they used that to sort of model these terrains. And these terrains have this sort of like ropey swell shape.
Who controls the accuracy of the heat flux measurement?
A lot of numbers, a lot of rheological parameters that were determined in the laboratory in the 1980s by this one group. There's a lot of arm waving here.
Okay, but when we switch from one group to the other group to the other group,
They're all using the same rheological parameters because they were all from that one
they're,
paper.
They're all, in one sense, locked in accuracy space. They may all be inaccurate, but they're moving in a locked way, right?
It's good logic. The only difference is that these people are using topography to infer this elastic thickness. They're using topography to inform a model that's forming these features. They're going about it in slightly different ways. And this group also made these measurements of heat flux over these 3 areas and averaged it together. And I haven't had a chance to email them to find out what the results were for each individual area because I'm very curious. Because you can see 110 to 220 sort of nestles right into that range. And this area here is this area. So it's entirely possible that their number here is higher than their numbers here. And averaging those together really just lost us some resolution in that data and just lost us some data points. Because I would argue that the ages of these different areas might in fact be different. They might not be related. And so yes, exactly, that was going to be something I was going to bring up. This is a problem. This nestles right into the next range that I haven't shown you yet, that I just accidentally showed you. It nestles right into this range right here. So I don't have an answer for you yet. But to a certain degree, they're all using the same rheological parameters from this one. We were talking about this earlier today. There's this one paper that this one group did, and they did a bunch of experimental measurements, and that seems to be the place where everybody's getting these rheological parameters in order to make these measurements and infer these heat fluxes. That's problematic in its own right, because time has evolved, experimental techniques have evolved, we can do better. So I want to leave time for questions, so I am going to blow right through this. Okay, so crater terrains, we know the crater terrains are older. So I thought this was really interesting because they did some modeling, but they were modeling craters and not fractures. Does that make a difference? I don't know. They get a heat flux of 150. The crater terrains are considered to be older. They did not report an elastic thickness, so I couldn't tell you whether or not their elastic thickness is growing, right? We've got a thinner shell here. Is it thinning within the parameters? I got to work on that. But I was just mining the literature because I was very curious because I had noticed that a bunch of people were doing these measurements on Enceladus, and I said, well, wait a minute, where are you doing them? How are you doing them? And whether or not you're can we already start to see some changes in Enceladus? So I think I would argue that it's hard to do it here because you have different terrains being averaged. But I want to show you Dione because I think it's a little bit easier to see in Dione. There's still some arm waving, but I'm starting to think that we can see what I was hoping to see, which is a change in time. So Dione, really old. You guys have seen this feature. It's a ridge. They use topography here to look at the flexure of the ice shell. From that, they were able to get an elastic thickness. They estimated about 3.5 kilometers. And from that, they estimated a heat flux of 25 to 60. Now, it's not that straightforward either because we have different creep regimes. And so they looked at 4 different creep regimes at 2 different elastic thicknesses. Let's just look at the yellow box. The yellow box is the entire parameter space that they explored that fits within this range of 25 to 60. It's an awful lot of the parameter space. That doesn't bode well for me in trying to make these calculations on a younger feature and be able to actually see some kind of difference. So I'm using a really young feature. I didn't use topography because I didn't have it at the time. This is topography data from Bedingfield et al. And she actually looked at the topography of these different fault scarps on Dione because she wanted to see what their slopes were. Now, these fault scarps theoretically should form at about 60 degrees. It's what we know about fault mechanics. Normal faults should form at about a 60-degree dip. She actually found that they weren't forming at a 60-degree dip. And she hypothesized that the reason they weren't forming at a 60-degree dip was in fact that they were forming at a 60-degree dip, but they were viscously relaxing. Viscous relaxation is a problem that we have across the icy satellites. You've got these craters on Enceladus that are just rims. There's no floor, it's just flat and a crater rim. So the relaxation is a process that's modifying these surfaces. So her hypothesis was that we have fault scarps on Dione that aren't forming at 60 degrees, or aren't being preserved at their 60-degree formation angle, but in fact they are forming at 60 degrees. So I'm going to try and jump ahead. This is a plot of blue is showing you the work from Hammond et al. In 2013, and orange in this case is my measurements based off of the elastic thickness that I inferred from this region. And these regions are these really beautiful young graben, and I inferred an elastic thickness of about 6.5 kilometers, so thicker than what Hammond et al. Found for that large ridge, which is not intuitive. And then we see that generally speaking, Hammond et al.'s heat fluxes are estimated based, regardless of creep regime, are a little bit higher. So here's that yellow box. This is that 25 to 60 that they estimated. That's my box. I should have overlapped them now that I think about it. So you could have just seen both of them at the same time. I'll just have to flip back and forth. So that's their regime in their parameter space that they think best represents the heat fluxes that would have happened at their really old ridge. And those are the ones that I think are happening at these really young graben. I don't know, are you guys convinced? I haven't decided if I'm convinced because I'm not kidding you. I did that like at 9 o'clock last night. So it's still really fresh. So if you guys have any cool ideas, please let me know. I'm really interested. So to sum up this part, I think I'm starting to come up with this way that we can actually start to look at changes in the brittle ice shell thickness and changes in the heat flux through time. It needs work. But people aren't asking the temporal question because it's hard. And they want it to be really precise. They want to be like, it's this and then it's this. And that's just not going to be the case. So we need to come up with these techniques. Let's put some bounds on them and then look at these relative changes and actually say, okay, 25 to 60, that's a big range. But if our next range is 10 to 35, maybe we are seeing a trend. But 2 data points, you can do a lot with 2 data points. You can say a lot of things with 2 data points. So it's complicated. And I thought I put in a Europa slide for you guys. I don't know where it went. So Cassini's over. We learned so much from Cassini about icy satellites that it's in part helping us drive this mission to go back to Europa. We now need to ask questions like, how homogeneous is the ice shell? Are there any density contrasts within that ice shell that are changing what we're actually seeing? Because right now we're just treating this as like a really homogeneous, like 4-layer onion. And that's just not the reality. And so I want to take some questions. I want to hear some feedback from you guys. There's a lot that I still haven't figured out with this stuff. but it's this idea that me and some of my colleagues have been really thinking about for a long time, and we're trying to figure out how we can start getting at this temporal component, because we think there's enough data here for us to start looking at some relative changes. But there's a lot of work to be done because there's just a lot of free parameters in this stuff. Questions? Sorry, I got caught up.
That's good question. So what would you guess?
Well, are there any models that anybody has made that looks at how this non-synchronous rotation and how the outer shell may be moving with time? Because if you say it was 120 degrees to shift these, and if another model says 120 degrees was this long ago.
Yeah, so when we model it, we actually set a period. And that period is usually in a range of about 10,000 years to about 10 million years. Although 10 million years isn't really feasible, it's just this end member we always throw in there. About 1 million years is more likely. So we look at that. It doesn't change the relative pattern, if that makes sense. Changing the period doesn't change the orientation of the features in which they form. It just changes the rate at which they form. So it's kind of hard sometimes to test what's the most realistic. So nobody's actually looked at how to piece that out from the fracture patterns in particular, because I think it's relatively subtle. So it's one of those really big challenges that we have, and sometimes the rheology can help you nail that down a little bit better. But nobody's looked at that specifically.
Not really feasible to try and pull the age out of that.
Didn't John Kay do this with Simon? Troughs on Europa. I think there's a master's thesis. I can send you a link. Yes.
Okay.
So you showed a picture that had like 50-kilometer diameter craters, I believe, just a couple ago. I'm just surprised that none of these craters pierced a thin ice shell. Even here, like there's some craters that are 20 kilometers long. And so if the shell is, a few kilometers,
Yeah,
is
so
that
that's
possible? I don't know anything about the crater physics.
Yeah, so I don't know a lot about crater physics either. The idea is that people think that the ice shell in the crater terrains is really thick. And that's one of the reasons we still have the craters there. And that's why it hasn't been tectonized yet. It's just too hard to crack it because it's just too thick. My argument against that is, well, then why do we have all the pit chains forming in the crater terrains, which are the youngest features next to the tiger stripes? My argument is they're the youngest next to the tiger stripes. So why do you have them forming predominantly within the crater terrains? So I think one of the ideas is that the ice shell maybe is thinning, and that's why these craters are relaxing in the same way, because you no longer have that ice shell to support the topography that you would have with the 40, 50 kilometer crater. So it's a really good question. I know on places like Europa, there's a bunch of craters that were really very big, and when the ice shell of Europa was really very thin, you can actually see where it kind of like punched through, sort of like dropping a really big rock on a really thin ice shell in a puddle. You get that very characteristic pattern, and you can actually see that on Europa. It's actually been preserved. So I don't know of anybody who's actually started trying to assess what the ice shell thickness was when these craters were forming, and maybe how that ice shell has changed as these craters have sort of eroded. It's not the best word because you think of sort of being destroyed, but sort of being eroded by viscous relaxation. I don't remember whether or not this Bland paper at all really spent any time talking about the ice shell thickness. They spent most of their time talking about, do they look this way because they're being viscously relaxed, or do they look this way because they're being mantled by material that's falling out of the plume? And the answer was sort of, well, it's really hard to make them viscously relax unless you have heat fluxes that are this high. And the only way to get heat fluxes this high is pretty much to not have an 80-degree Kelvin surface temperature. Now you can solve that problem by putting a bunch of material on the surface and insulating the surface, but it's still, how do you get craters to look like that? And how do you separate the signal of viscous relaxation away from infilling from the plume material?
Wondering about any correlation between crustal thickness, crustal ice thickness, and this superficial heat flux. And if you could actually sort of figure out how thick this ice sheet is based on how much heat is coming out?
So the way this has been calculated is you actually find out how you do whatever magic you do to estimate the ice shell thickness, and then you run a calculation to calculate the isotherms, the temperature at the base of the elastic layer, and then you calculate the heat flux. That's how we've done it here. It doesn't mean that that's the only way to do it, but we're trying to infer this from a photograph of a surface. And so we're making a lot of inferences, we're making a lot of assumptions. And that's why I kind of was a little like, do I want to present this story? It's kind of new, I'm still waving my arms around it. But that's kind of why I wanted to present it, because I wanted you guys to find all the holes in my assumptions for me. Help me out with that before I really start pulling this out on a higher, because I think it's important to kind of put that new stuff out there, find out where the holes are so you can start stopping them up before you get too deep into the project and have somebody sort of check your assumptions.
Ignorant question. I'm thinking about the history of Enceladus as a giant heat source. According to Wikipedia, Enceladus has a 2-1 resonance with Dione.
That is correct.
Okay. Do we know how long that has been the case?
Somebody might. Somebody might.
Yeah.
So before we arrived at the Galilean moons, amazingly, somebody had predicted that Io would be undergoing volcanism because they calculated the energy involved in the tidal forces. This is just, I'm begging to find out, do these heat fluxes, which I'm thinking you must relate to tidal production, has anybody calculated whether or not one would sustain some sort of heat flux, the global heat flux associated with tidal forces?
So you can calculate what you would expect at Enceladus, and they did so in the 80s. And yeah, these numbers are not easy to make happen and not really doable with just tidal stresses.
Right.
There's something else happening, and we don't know where it's all coming from, really.
Or it's highly inaccurate.
Sure, that's always a possibility. It's always a good check to make.
Were you assuming a global ocean, or that perhaps the southern actually has like a thicker ocean and the northern maybe doesn't actually?
Yeah, so it's likely that it's thicker at the South Pole. Our model doesn't have that capability to sort of make it thicker at the South Pole. If you want to do just our model will actually, you guys can download it. SatStress GUI. It's on GitHub. My colleague Alex Padoff has been the one who's been sort of keeping that up and running and constantly approving it. So if you have ideas, email him. Don't email me. I email Alex Padoff. He will kind of add it to the list of things. I mean, this is something that he's funded to kind of maintain for everybody and make sure that it's really user-friendly. So go download it. It's got a really great GUI. It's very useful. Anyways, you can do a regional calculation. And so you could actually put in, say, hey, I want to look at just the South Pole. I want the ocean to be this thick here. But you're still making it that thick everywhere. So it depends on what you're looking for. I mean, what is it? All models are wrong. Some are useful, right? Like, it depends on what you're asking of the model, right? And I'm always asking the model, I'm looking at the global distribution. So there's some parameters that are just not particularly sensitive when you're looking at a global distribution. But when you're looking at more of a regional distribution, you can actually use the model to start to get at what period might make more sense and what the ice shell thickness might be. So the model just doesn't have that capability. It's a very symmetrical model. Did I keep you from snacks too long?
Oh, yeah, sure. But can I keep us longer? I was about to ask something that's fine. But I had another thing that I was curious. The speed change. I mean, I often hear about them in volcanic environment has been like collapsing, so you have intrusion on dikes or things on tracks. What's going on to produce this type of feature in an icy satellite, which I don't imagine has a lot necessarily of very loose material at the surface?
Fun fact. Part 2 of my paper actually shows that so the first part, this paper, my paper from this year, proves that these features are tectonic. And they are forming because you have a crack in the ice shell, but that ice shell is mantled by a layer of loose material. Much of it is plume fallback, although a few hundred meters of it, up to a few hundred meters of it, could be impact-generated regolith. There was some calculations in the late 80s that actually said up to about 200 meters of material. And so I actually, the paper that I kind of go through, could they be karst? Could they be volcanic vents? Could they be this? Could they be that? Because you can form pit chains from, there's like 8 mechanisms minimum that you can form pit chains, because pit chain, the definition of a pit chain is a bunch of pits in a linear assemblage, right? I mean, so the formation could be due to a lot of different things. So I kind of go through all the arguments, and really I think one of the most convincing arguments I think of is their distribution. I mean, it's parallel sets. I mean, they're not radial to anything. They're not related to any kind of flow feature. They're relatively regular. They don't have a raised rim, so they're not secondary. And so they're really being generated by tectonics in the subsurface that are being overlain by a layer of loose material. And that loose material is either or both impact-generated regolith in addition to plume fallback. And there's been models of plume fallback distribution on the surface. And so what I'm doing in this second paper that's very close to being done is actually using those pit chains to actually try and probe how deep that material is, and actually looking at the distribution of that material across the surface, at least where we detect pit chains, because of course if we don't have a pit chain I can't make a measurement, and actually trying to do it that way. So we think there's actually a lot of material in the surface, and I'm just starting to think about, after a talk I saw last week, I'm just starting to think about how sintering may actually help us achieve those depths in terms of what we're observing. Yes?
I know this is so removed from where you're actually getting data, and it may be too complex for the models right now, but is there any concern about, you've got the stuff going on the surface, but delamination from underneath, and maybe that's producing different thicknesses of the shell? I don't even know what mechanism would cause
Delamination
of the ice shell itself. And so the different regions might actually be reflecting internal thinning of the structure of the shell, and therefore the flux might change because you've got less thing, but it's not being imposed from the outside.
Well, so, you know, the chaos terrain on Europa is actually a really interesting study for something like this, where we think that chaos terrain, pits on Europa, spots, domes, they're all kind of these places on the surface where we think that there has been heat from the ocean somehow making its way closer to the surface and manifesting that heat by sort of melting the surface. And in some cases just melting a little bit, and in some cases melting it a lot and sort of breaking up that ice shell into all of these sort of floating chunks of icebergs. The idea being that perhaps there are lenses of ocean water trapped in that ice shell manifesting itself on the surface. There's a paper by Brittany Schmidt in 2011-ish in Nature where she kind of goes through this idea of having sort of these lenses of water in the ice shell. And I think everybody assumes that the ice shell is in fact very heterogeneous, but we have no way of getting at that other than saying we have a feature here, we have enough data here to make an estimate about maybe how deep that feature goes and maybe making a guess about the ice shell thickness, which then tells you maybe what the rest of your profile might look like and how thick your ocean might be there. Europa Clipper is going to do this for us at Europa. And this is what I mean, like, Cassini was so successful, and this is why comparative planetology is so important. Galileo showed us a huge amount of data and showed us a huge amount of information, but it still wasn't everything. 10% of Europa's surface, right, was imaged at resolutions good enough to do geological analysis. So when we went to Cassini and we got even better data, mind you, like, did any of you in the back ever have a flip phone with a camera on it? It was like 1 megapixel, right? I mean, we all remember flip phones with megapixel cameras, but I wasn't sure. That's the camera on Cassini, right? And we still did this stuff. That's the E-ring, by the way, the fuzzy blue thing. That's the E-ring. Enceladus is doing that. 1 megapixel camera, right? This is a mosaic. now that we know that, we can make comparisons between what we know about Enceladus now and what we don't know about Europa, and that's informing how Clipper is being designed. So some of these questions about ice shell thicknesses and deviations in the ice shell thickness, and what does that structure look like? There's a really beautiful radar instrument going on Clipper so that we can actually answer some of these questions, and that's going to inform how we think about all the other icy satellites and how we modify these models to understand these internal structures.
Right, well, on these words, I think it's a great moment to transition to explore some slightly enhanced water.
Thank you guys, thanks for being patient with me.